Innovation Zero Ideonomy is a collaborative innovation community that will bring people together across sectors to solve problems supported by machine learning and AI. So you'll see QR codes dotted around the event where you can submit, view, and rank the most important problems across each forum. And this will create a prioritized list of problems so we know where to focus on in our innovation efforts. After the event, we'll set up a series of new problem-solving teams where you can meet people who share the same problem as you, regardless of what sector you originate from. We'll then connect problem owners to solution providers so we can solve problems together, creating a new global community for positive change. So yeah, please scan the QR code to get going. And our next session is Circularity, Decarbonisation and Defossilisation for the plastics value chain with hydrothermal advanced recycling. May I present to our speaker today, Dr. Geoff Brighty, Head of Sustainability at Mura Technology. So over to you. Thank you.
Thank you. Okay, can you hear me okay? In the back? Okay. Well, thanks for coming. I appreciate I'm at the graveyard slot after lunch, so hope you've had a nice lunch. I hope this will be some entertainment for you. Can I just quick show of hands? Who here has never really come across advanced or chemical recycling? Okay, so looks like most of you at least come across what the sector is trying to do and the technology. So I'm going to talk about our technology and our business model, but I'll talk also a little bit about advanced recycling and really how, as a disruptive sector, it's really trying to steal a march on the historic ways we've managed waste, particularly waste plastics, in the rounds. So I'm Geoff Brighty. I said I'm Head of R&D and Sustainability at Mura Technology. Been involved with the company about 5 or 6 years. Before that, I was a regulator with the Environment Agency and then worked for an NGO called Plastic Ocean. So I've spent a lot of my life dealing with waste issues and then dealing with the pollution aspects and the impacts of that. And my sort of personal journey on this is really to understand how on earth we can go about fixing it. And one of the challenges we've also tried to deal with is not just the solid waste problem, but now, of course, it's through the lens of carbon. You can't just solve one problem and then start to create or exacerbate others. So what I want to take you through really is a journey of how Mura are looking at this from the point of view of the waste management and circularity point, but also the issue of how we do this in a lesser carbon-intensive way. So that's really what our mission is, and our vision is basically we want to be the global market leader, provider of premium circular hydrocarbons. So we don't see ourselves as a waste company. We're very much in that how do we support the circularity piece, which is increasingly coming through now in regulation. So 2 weeks ago, European Parliament voted on something called the Packaging and Packaging Waste Regulations, which is mandating recycled content in future packaging by 2030. And if you're a brand and if you're putting packaging on the market and you don't have that content, then you are barred from putting your products onto the market. So it's a big deal for a lot of organisations, but also automotive. It's not just about packaging. There's a bunch of sectors that are now crying out for recycled content into their products. And that's the aim that we want to fulfill alongside a number of other companies in this space called advanced or chemical recycling. Just a little snapshot about Mura. So we've been going about 7 years now. We have a protected technology that was born out of the University of Sydney in Australia. The technology is based on water. So this is water under very specific conditions, which I will elaborate on. So it's quite different from the point of view of how we try to deal with the plastic waste and convert it back into something useful. We are supported by a number of strategic investors. So you can see the logos there, but also with KBR, who are our global build-out partner. So the business model for Mura is kind of a twin track. One is to build and operate our own plants, and we're focusing really in the UK, EU, and the US for that. But also, we want the technology to get out there for a variety of reasons. One is clearly we want to address the plastic waste problem, but also de-risk the technology. So the more plants we build, the more we learn in different locations with different challenges. And we're doing that with a company called Kellogg Brown & Root, or KBR, which you may be familiar with. The focus of the presentation really is about sustainability. So how do we decarbonise and do circularity simultaneously? So I'm not going to dwell too much on that. But we aim basically to create what they call a whole product solution. If you think about this in terms of circularity terms, and this diagram kind of helps that. traditionally we've been in that first loop. We've been in that sort of take, use, dispose, and somehow then it's lost to the system. So some material is going to go back through a mechanical recycling route, and that's fantastic. But a lot of material we know is being lost to the system. And that is being lost largely to things like landfill, which is very big in the United States, less so in Europe now. We know it gets in the environment. I spent 6 years campaigning for this issue, and it's getting everywhere. It's on the top of Mount Everest, it's in the deepest oceans, it's in the poles. We know plastic is ever present. But it's also going to energy from waste. And energy from waste is a massive challenge for us because we're burning this material. It's seen as a good thing to do. It's energy recovery, but of course we know that that is carboniferous. We know it's emitting carbon to the environment. So what advanced recycling is trying to do is to take that material that's otherwise lost and bring it back around a circularity route. So by doing advanced recycling, and then if necessary, depending on the quality of the oil, some upgrading step to clean it up, but to make that as a drop-in solution for petrochemical companies to take that material and then reprocess it. So we're partly defossilizing, we're displacing fossil oil coming out of the ground, but then also we're providing a feedstock which will meet the requirements of technical applications. So for example, packaging for food, we know it has to be single use because of the hygiene and barrier properties it needs to bring. We're able to bring back a feedstock that can be used to make that packaging. Similarly, automotive, you wouldn't want too much recycled plastic going into a car without knowing it was actually going to do the job, like crash protection, for example. So this is the ecosystem that we and other companies in the space of chemical recycling fit. What we're trying to do by our approach then is to give that opportunity for that material to come back around the loop, be reused, displace fossil oil, not challenge mechanical recycling. If anything, we're actually helping mechanical recycling. That's not always what mechanical recyclers think or say, but the aim of that is to do two things. One is to make sure that we're getting back the material that they're otherwise paying to get rid of. So we're taking that material at a better price, or hopefully a lower cost to them to take that material on. But also we're giving them an opportunity to invest in more better technology. So we're creating a valorization and a potential for growth. And when you consider in the UK, we say we recycle about 50% of plastics placed on the market. Actually in the UK, a third of that is going abroad. So we're down to in the 30s in terms of what we actually recycle. We've got a long way to go. And it's a rallying call for mechanical and advanced to better work together. And as I said at the beginning, to provide the material then goes into future packaging, like packaging and packaging waste regs are going to require us. So a little bit about the process. I've already mentioned the fact that it's based on water. So we will take, I'll go through the feedstock in a moment, but basically we take shredded post-consumer waste plastic. Doesn't have to be washed. We don't wash the labels off or the food contact material. It's put into an extruder where it's heated and pressurized, and it's mixed with supercritical water. So high pressure, high temperature steam, 300 bar, 450 degrees. And that melt flow goes then into our hydrothermal reactor at these very high temperature and pressure conditions. Reaction time is about half an hour. That time is enough to basically break the polymeric structure of the plastics into short chain hydrocarbons. So we're going back to short chain hydrocarbons. They're not monomers, it's hydrocarbon material. The system is then depressurized, and the gas is then enabled then to be depressurized and then goes into, through boiling points, it's cut into different products. And I'll come on to those in a moment. So these are hydrocarbon oils and a processed gas. So from start to finish, from extruder outwards, it's probably about 45 minutes for that melt flow to get through and then come out the other end. It's a continuous flow process, and I'll come on to some of the advantages in a moment. But what we're trying to do here essentially is to do as little as we possibly can to the plastic as it arrives in bale form at our site. We don't want to spend time and energy and cost, therefore, to clean it up. Our process, being water-based, is able to deal with a lot of those contaminants. So, I'm not sure that's coming through very clearly, but basically we've got a number of potential advantages by using water. So I guess our nearest competitor process would be pyrolysis, where you're basically heating plastic in the absence of oxygen to create a gas that you then condense and to create the oils. The problem for us is, in this space, is that by doing that, you create a waste, you create a char. So by basically melting the plastic into water, we don't heat the plastic, we heat the water, and the energy transfers then into the plastic via the water. And that means you have stable reaction conditions and efficient heat transfer, and that means you don't end up with any waste, solid waste coming out. Also being based on water, you can then scale the reactors. So we start at 20 KT, that's our first plant we're building, which I'll come on to in a moment. But we can also go to 50. Pyrolysis is probably sort of 15 to 25 kilotons per annum output. It's about as big as they can get. And we know we need 500,000 tons of recyclates to go on the European market just for packaging. So we've got to try and get that material out. It's tolerant to mixed plastic waste, so we can take mixtures of polyolefins, so both polyethylene, polypropylene. It's a water-based process. We need to dry the feedstock and creates very clean hydrocarbon products. And it's partly because due to the water, because the water, some of the ionic material will partition to the water phase. So we believe that that material will then be, the oil then going on will need less upgrading or less treatment beyond. And I'll touch on sustainability as we go through. The other one is that one of our products is the heavy wax residue. And in plastic, you have a bunch of materials in there, not just the polymer. You have things like solids, like fillers and colorants, and that's where that material goes. So let's look at what we produce, what we process. So this is the typical ways. These are bales on our site that we are now looking to put through our plant. So it's mixtures of polymers, high and low density polyethylene and polypropylene, but also co-mingled PET film. We wouldn't want to take bottles. They should go to a mechanical route. We would always exclude those. But we're also tolerant to polystyrene in low quantities. Or post-consumer. We could take post-industrial as well, but that has different issues around things like EPR. So it's residual material from waste sites that is not recycled, and we know we're taking our material that would otherwise go to energy for waste. These are the products. So from the top line, you've got the naphthas, and then into distillate gas oil, then you've got a heavy gas oil. At the very far end, you've got this heavy wax residue. So the liquid fractions, about 80% of our yield, will go around the circular value chain. They'll head up, going around to plastics and other manufacturing processes, going into a cracker, potentially into refineries. So these are circular products that are going to go around into new products. The heavy wax residue, though, has a different route. That's going to be used as a bitumen binder for asphalt. So it won't be used in circular products. It could be cleaned up, and it'd be quite energy intensive to do that. But actually, we've got an off-taker that wants to take that material. So the liquid products are going to Dow and Neste in Europe. We've yet to announce our heavy wax residue off-taker, but they're a major asphalt manufacturer in the UK. We also have a process gas. In the first site, we're recovering that for energy to heat the high-pressure boiler. But in future plants, we'll look to recycle that. And so, therefore, it's important that we're linked or connected with, and obviously on the same site of a cracker complex. So the next site we're building will be in Germany with Dow on their Boland site, and we can just pipe the gas straight into their ethylene cracker. So that's the sort of the surround of the products. Our overall yield is, so for every ton we put in, we're able to get over 90% hydrocarbon out, which makes it very efficient. We don't create a solid waste. So that's the site of our plant. So you can see our reactor in the middle there. That's the cracking tower where obviously depressurization and fractionation happens. And these are the storage tanks. So over here at the far end, you've also got the material preparation hall where the bales are dry cleaned and shredded, ready for processing. The plant is 20,000 ton capacity, expected to go live midsummer this year. So we're in the final stages of commissioning. We're commissioning the front end. We're now in the commissioning of the back end. So this is the first. There are two others under build at the moment. One in Japan, one in South Korea. Both of those under license. So with KBR, this is our first commercial build to be online this year. So to sustainability, the part of the challenge that we face is if you're going to start talking about your sustainability credentials, you need to find partners to do that with. If people don't believe you, if you just put something out in your own name, it doesn't have the credibility. So we've worked with a whole range of different partners, some of whom are commercial and some are independent from the point of view of their basic funding. So we've had Innovate UK funding to support the work with WMG, but we've also supplied data to third-party independent assessments, so European Commission's Joint Research Centre, Sfera, working with the Consumer Goods Forum, who have been working on a piece of work that was produced about 2 years ago, and also working with CFlex, which is a flexible packaging value chain consortium based in Europe, which is looking at the sustainability of flexible packaging and how to make it more sustainable. We've just announced a couple of weeks ago a collaboration with the University of Ghent, who are probably the world leaders in chemical recycling. They may be known to some of you. And that will be very much used to build using that collaboration to build a plant in their research facilities. So we're able to run parallel trials with pyrolysis and also do things like hydrotreatment and then cracking. So we're able to do from start to finish the whole process to get then to an ethylene cracker. So these are key important partners for us. We can't do this on our own, and we're very grateful for the support we've had from Innovate UK, particularly for the WMG work. And I'm going to take you through, we've got 4 slides with some data on, which will give illustrations of how we fit into the ecosystem, and then also really how we can start to decarbonise. And that would apply to the whole sector, not just to our company. And I would say, as a chemical recycler, advanced recycler, whilst it is disruptive, there are a bunch of technologies out there. I'm involved with an ISO committee on chemical recycling. There's a whole range of technologies out there, and each will have its role to play based on its operating scale, the material it can take. And with Ghent, we're looking to take different materials. So we're looking to potentially process things like ABS, polyurethane, rubber, and potentially even composites. So we think the technology could be used for a whole range of different materials. We've started with something quite straightforward, which is polyolefins. So, question, is it better to sort or to burn plastic? And this is kind of where we start the journey here. We're trying to divert something from energy from waste, what works out best. If you burn a ton of mixed waste plastic, it's throwing out a little over 2.3 tons of CO2. Bearing in mind that energy from waste pellets, about 15% content of plastic, but it's around 60 to 70% of their CO2 emissions. So getting this plastic out of energy from waste pellets is really important from a point of view of decarbonising that sector as they're headed towards ETS. But actually the carbon benefits are huge. So we process, for 1 tonne of that processing costs us about half a tonne of CO2. So there's a net benefit, this sort of counterfactual scope 4 saving of about 1.8 tonnes of CO2. So the key question really is, do we want to sort this and put it into a value chain that can come back round the loop, or do we just want to recover the energy? And it makes no sense to burn plastic. It's worse than burning coal. Why the hell are we doing this? Energy from waste has its place. Let's put more biogenic material into energy from waste. I speak as a former regulator of energy from waste plants, and they do suck in lots of waste that perhaps they shouldn't be taking. So this is an opportunity. And from a 20,000 tonne plant we'll be operating, that's 40,000 tonnes of carbon saving just on the avoided carbon, which is kind of our gift to the nation and to the planet. And when you get to scale, and our next scale plants are, say, the 100,000 tonne size, we're talking over 120,000 tonnes of CO2. That's a massive saving. So in then comparison terms, how do we then compare to energy from waste and also the other processes? And this is really where I think some of the efficiency opportunities are coming, and all the technologies are looking to maximise their efficiency. This was a snapshot study done by European Union that was published last year, and we all submitted data sets. So compared to incineration, our process came about 60% less carbon intensive, so it's the same ballpark as our own study. Against 2 pyrolysis technologies that were submitted, we're about 50%. That's not to say you can't decarbonise a pyrolysis plant. Of course you can take green energy, but from a net intensity point of view, we're coming out about 50%. And that's partly because of our yield it seems to be higher than what pyrolysis is currently doing, but also we think our energy consumption is less. So on a per unit basis, the hydrothermal process that we operate as HydroPRS has a really good carbon footprint just from an intrinsic value. It was also the lowest in terms of acidification, and as far as I remember also it was the most resource conservation, it had the highest resource conservation values as well compared to all the other treatments, including mechanical recycling, funnily enough. So in comparison to other technologies in incineration, it's coming out pretty strongly. This was, came out last year. But there's a question of, well, so what? You're producing an oil that comes out the other side. How does that compare to fossil? And I mentioned about decarbonisation. It's one thing to sort the waste problem out. You've also got to demonstrate you're delivering an oil at a lower carbon footprint than what's otherwise available through the regular fossil route. Recently, the methane emissions were recalculated. They came out in EcoInvent 3.10, I think, or 3.12, whichever one it was. It's on my slide. But what it basically showed was that there had been a 105% increase uprating of naphtha carbon intensity over what was existing. And that's because people were not accounting for methane emissions in extraction and then in processing. So when you then compare the products of all chemical recycling products, you would see that there's a massive benefit to go to this recycling route. So we know that just on the EU grid, the UK grid, we're able to reduce the carbon intensity by sort of 40 to 60%. And if you go to a renewable grid and we're looking at different sourcing of material, our carbon footprint would come down to around 80% less than the fossil equivalents. And this is hugely important because if we're displacing a material on the marketplace, we also want to help people with their Scope 3 emissions in terms of their assessments. So our Wilton assessment done by University of Warwick will be an eco-invent, the next inventory that comes out. So people will be able to put in a carbon calculation for their product carbon footprint, and if you want to look at recycled content, what that 10% would look like, we will be in there. We're the first chemical recycler to do that in eco-invent. So hopefully we're beating fossil from the carbon point of view, having avoided all the other carbon. And then the next question then becomes, well, so what? In the scale of waste management, we know what we're collecting, but what is the potential for decarbonisation of the waste industry as a whole? So the study from Warwick carries on. If you extract and then make plastic and then make products out of plastic and then use the ones to throw them away, the cost of that carbon cycle has been verified also with the waste NGOs in the UK, and obviously it does align very well with work that was done by Consumer Goods Forum. It's about 5 tonnes of CO2 per tonne of plastic, which is a lot. That's a single cycle, 5 tonnes. If you mechanically recycle all that you can mechanically recycle of that plastic that's been placed on the market, this is kind of the typical distribution of plastics placed on the UK market, that comes down to a little under 3 tonnes of CO2 per tonne. So mechanical recycling is avoiding some of that material then being burnt, or sorry, not being burnt, as in being lost. That material can be brought back into future products, saving 2 tonnes of CO2. That's really good. If you throw in then mechanical and chemical recycling, so our process that's taking as much of the material that's being sent to energy from waste as we can, and put that through our process, your carbon intensity of your ecosystem drops to about 1.7 tonnes of CO2. So that's about a 40% saving over just mechanical recycling. So we are additive to the system. This is why everybody talks about, which is best, mechanical or chemical. They're doing different things with different feedstocks, bring them together, bring them to scale together, because they're sort of supportive of each other. We believe that this is quite persuasive to help decarbonise the waste industry, as well as we discussed also the energy sector as well, and obviously our Scope 3 going into the chemical sector is reducing their carbon intensity too. So at a system scale, it's making potentially a very big difference to the carbon intensity. And when you bear in mind that UK is short on its targets, or ability to meet the targets by 2032, they've got some carbon gaps. If we brought chemical recycling to scale in the UK, we would absolutely smash that out of the park. We could guarantee we could reduce the carbon intensity if we recycled all the chemicals, recycling that we could get our hands on, all the plastics we get our hands on. This is my last slide. So our process, partly because it's water-based, partly because it's efficient, is coming out at a much lower carbon footprint, certainly than incineration, and certainly lower than pyrolysis in conventional terms. That's intrinsic carbon intensity. You can reduce all carbon intensities of all processes by different grid arrangements. It also has a credible pathway for us and our partners to get to a low carbon circular economy. So we believe this is the most important thing. We just don't want to provide a material onto the market that is not helping people decarbonise their packaging, for example, or automotive. We know there's about 2 to 2.5 million tonnes of demand for recycled materials from plastics in the European Union going forward. That's partly automotive, partly packaging, and that's only going to grow by 2040. The target's going to increase, become more stretching. So the challenge is we need to get chemical recycling to scale now. We've got a bit of a race to get to that first hurdle or first target at 2030, and then we carry on. And then the final point about resource efficiency, we want to keep oil in the ground. The more we can keep going round the loop, so we're looking about, for every turn of our cycle, in terms of plastics, we're bringing out about 800 kilos. So every tonne, 800 comes back. Some losses in processing further on, but for every tonne, we should be seeing 700 kilos of material ending up in recyclable content. And that's a lot. So it's worth doing, and the attrition is relatively small. And that's it. Thank you very much for listening. I'm happy to take some questions. I've got 5 to 10 minutes.
Thank you. Hi. Two questions, if I may. One is, does this process mean that plastics are infinitely recyclable? And the second question is, have you considered the problem around water scarcity and whether this process might become one of those, like mining, for example, that becomes very water intensive and create that problem?
Yes, okay, I'll deal with the second question first. So I guess the question is, so what is the use of water in our process? And we used about 2 cubic meters an hour for the 20,000 ton plant, so it's relatively low compared to some of the other bigger consumers. And we're at the Wilton site, so we do have available water, but because it rains a lot in the northeast apparently. Sorry, Kim. My colleague Kim from Tigbits. But so water supply is always going to be a question. It's ultimately on our scorecard for our LCA. You've got 19 categories. What are your top 3 or 4 waters right up there? We treat and then we put that straight into the environment. So we have a very stringent environmental permit. So we have to treat to a very high standard. We're using BAT treatment to basically make sure the water is safe to go back in. It's going to tideways. It's not going back to fresh water. We are looking at recycling. And it's all about context, isn't it? I mean, it's it rains on us in the northeast, but we could put these plants somewhere else where water is a massive stress. And so wastewater recycling is very much on my radar as sustainability and R&D. Is like, how do we do that? So, Robbie, your first question. Sorry. So the short answer is our process would work with plastics that are readily recyclable that kind of gone to their end of life. So everybody's talking about reuse, and we're big supporters of reuse. We want to keep that material in use for as long as possible. But even at end of life, can we regenerate it? And the short answer is yes. This is a regeneration process of waste plastics. For us, it's like we don't want to see plastic come out of that cycle. So even if you have single use or whether it's reuse, but even there things come to the end of their life, we can back to reprocess that. The challenge is a lot of long-lived plastics aren't of HD or LDPE formats. There'll be other materials. So stuff in cars, for example, have a 20-year lifespan. So can we get that material back? And that's our research program with the University of Ghent. Once we built our reactor, we want to look at other value chains where they have a waste plastic challenge. Can we bring that back round? But yeah, we see ourselves very much as a regeneration step after multiple uses, hopefully long life in use. Thank you for your question.
Hi there. My understanding is that you're suggesting this as a complementary technology to mechanical recycling.
Yes.
Can you talk a bit about the kind of how those two technologies stack up and why it wouldn't replace mechanical recycling?
Okay, so the processes are doing different things. We could take very good clean material, that'd be lovely, and put it through our plant, and it would have a good yield and so on. The economics don't stack up. Some of the recyclates that mechanical are taking are £500 a tonne. That's out with our business model. We want to keep the cost as low as possible. Also, the material that we do take has a negative value in some cases. People are paying to get rid of this material, and we know when ETS comes in, that will be another price pressure on those disposing of that. The fact that our process can take that material and get a good yield off it, that makes economic sense for us to do that. In terms of the business models also, mechanical recycling facilities may cost 10 to 20 million. I'm not a mechanical recycler, but they're not hugely expensive to build and operate. Our plants are upwards of 220, 250 million pounds. So the capital investment is much greater. So we have to look at price pressure on feedstocks. That would be one of the areas where we're looking to minimise that. So I would say, whilst we could take that material, the material is not really available to us in the way we would like to take it at that cost. And the other thing I would say is mechanical recyclers operate at a much lower carbon intensity because they haven't got to heat the water. They're doing stuff like mechanical processes, which is much lower cost in carbon. So from a carbon point of view and from a price point of view, I don't see us having that crossover. There may be something in the middle, but I think we're targeting the stuff that's well away from where mechanical is. We're taking a diverted waste out of a MRF that's not going anywhere else except to a chimney anytime soon. So,
hi, thank you very much. My question would be around what do you see as the risk to being locked into a plastic-dependent society and economy, and the argument that some might say that it provides like a license to operate to existing petrochemical companies. And yeah, just any thoughts on that?
Yeah, I think that's a fair question. It's been one being put to me. I talked to an ENGO about a year ago, and I said, what's your policy on chemical recycling? And they said, we don't have one. And I said, well, why is that? They said, we don't want you to exist because of the very point you just made, which is you perpetuate flexible single-use packaging placed on the market. It's a regulated market, so packaging exists for a reason. It's there doing a job. So whether we personally have a view as to whether packaging should exist on the market or not, it is there, and it's required to give long shelf life. We all know that the carbon intensity of what's inside the packaging is way more than the packaging itself. That's kind of part of the argument. But PPWR, the new regulation coming into Europe, is trying to improve the sustainability of that and deal with the wastefulness. So we're kind of facilitating that circularity piece. That's not to say that we don't have wasteful packaging. I mean, we've all seen it. We've all been to supermarkets, we've all been to shops, and we think, why have they wrapped it in that? You know, you've seen bananas in plastic boxes. It's like, why? So there's an issue of elimination. I'm involved with the UK Plastics Pact, and target one is eliminate. Drinking straws, stirrers, and then you're into multi-layer packaging, which we can process, but it's very hard to recycle elsewhere. So I think there's a reduction of thought minds, which has to happen. Reuse is another way of thinking about that. But there will always be some flexible packaging which needs to be reprocessed. And also PPWR is demanding a recyclate. We're pretty much the only supplier, or our sector is the only supplier of that material to go around. So we need to make sure that that is supplied, so we are getting circularity. The other thing is, I was saying, in terms of that's packaging, we're not short of polymer wastes. And that's why they're working with the University of Ghent. Pyrolysis is being used for tyres. So we think our technology can also process tyres to get back the oil, which is biogenic in nature, but also some of the other components like carbon black. Energy intensity of carbon black is phenomenal. It's outrageously high. If we can bring back carbon black at a high quality, that'll be a massive carbon saving to the tyre industry. So I think what we're seeing with chemical recycling, as a part of Chemical Recycling Europe, is we want this sector to disrupt these existing waste loss systems, and can we bring back materials? And there's a massive appetite for the manufacturers of tyres and cars and packaging to bring recycled content back in. They're seeing it from their ESG point of view, shareholder pressure, as well as regulation. So let's minimise what's going on the market, all in favour of that, but let's make sure when it's on the market and we've pulled the oil out of the ground, we're keeping it in circulation for as long as possible. And that's kind of where my mindset is. In the sunset of my career, I should say. So I just recently turned 60. So for me, I want to make sure I've tried to do something that's really proactive and positive before I retire. Thank you for the question. My last one.
Hi, quick question. Are you combining, so you talked about LCAs, are you combining carbon accounting, so whole life carbon, with plastics and tracking the recycled content in plastics?
Okay, so just where we fit in the value chain, we are basically providing the recycled hydrocarbons that then go into the cracker and then come out the other end as ethylene and then polymerized. So that's our role. We're part of something called ISCC Plus. So for a bunch of reasons, so partly provenance, in terms of PPWR requires you to have post-consumer waste recycled content in the future packaging. So if we were taking waste, say, from automotive, which we're not, but if we were, that would not be allowed to be used in that future packaging. So our market we couldn't fulfill the market need. So we're focusing on post-consumer. We've got an end-to-end tracing of all the material, where it was collected, where it was processed, comes to us. We then have ISCC chain of custody, and then it goes out.
You're tracking everything, but you're not reporting on the whole life carbon. So in other words, something like PAS 2080, PAS 2080 is used in the construction industry because it is a very fragmented sector, and there's lots of subcontractors, and so it's tracking it from the design through the sourcing, through the build, through the use, through the end of life. So you're not doing that.
Well, so within our value chain, we are tracking absolutely everything, and obviously I'm doing the carbon footprint from when it arrives at our gate, including the transport to our gate. We've got a research paper, the Warwick data I showed you was a research paper, and our carbon stops at the gate, but we're now looking at what happens beyond. That's what we're doing up with the University of Kent.
I'll have a chat with you sometime.
Yeah.
Thank you.
I think that's it. So, thanks very much. Enjoy the rest of your day. By the way, we have a stand almost immediately below us by the side of the main stand.